Good morning, glad to see you all here. I'm going to talk about, oh dear, I can't see the screen from here, that's my problem. I can't, I'm not tall enough. Okay, so I'm going to talk about what we've learned from top-down inferences of surface fluxes. What Peter talked about is inferring, what Peter's focused on is the global carbon budget, and what I think we need to go towards is regional estimates of this carbon system. So here is the holy grail for all of us. The top is the emission, the green line is the emission, and so you can see from all the marvelous CO2 measurements in the atmosphere, we have the blue at the bottom that shows the atmospheric increase, and so the green is where the CO2 has gone into the land and the oceans. So about 50%, and the recent estimate is about 45, anywhere between, approximately half the CO2 that we've put into the atmosphere has remained into the atmosphere, and the rest of it has gone into the land and the oceans. And so here is the latest estimate from the Global Carbon Project. And so you have on the left the fossil fuel emission, about here is in gigatons CO2, so you have to multiply by 12 over 44 to get back into petagram carbon, which is our normal unit. But you see 91% has gone from fossil fuel combustion, and about 9% from land use change, mainly deforestation in the tropics. And so the atmospheric increase, as Peter has indicated, is about 44% from the direct measurement. And so what we have here is the bottom-up estimates. The ocean, so the ocean is the ocean uptake is estimated from, this is the average of quite a few ocean models used to calculate this. And then the land, as what Peter indicated also, is the residual that goes into the land. So our best estimate is about, I like to be democratic, so half into the atmosphere, a quarter into the land, and a quarter into the ocean, of that order. So to get to the fluxes, we have relied on the CO2 measurements, the flux network and the in situ network. And so we're very grateful to Peter Tans for making the data available to anyone, and so that we could get started on using this data to infer the sources and sinks. But by design, the observing sites are at remote marine locations, far away from the sources that we're after, the land source in particular, because the photosynthesis and respiration gives us a diurnal cycle of about, could be 50 ppm day and night photosynthesis, and we're trying to extract a trend which is 1 to 2 or 3 or 4 ppm per year. So the inferring fluxes therefore requires an atmospheric transport model. And so this is a plot I have from the last century. So this is an example. So if we put in 96% of the fossil fuel emission is in the northern hemisphere. So you can see at the surface there's a sharp gradient across the equator. That is because of the ITZZ, there's a barrier to transport between the hemispheres, and that barrier is of order 1 year. So the zonal mixing time is about 2 weeks, and within a hemisphere it is about 3 months, and across the equator it's about 1 year, of order 1 year. If we look in the vertical, then you can see here in this model we release CO2 in the mid-latitudes, and you can see how CO2 goes across to the other side. There's convection that mixes the CO2 in the vertical, and there's a fast elevator here that in the intertropical, the ITCZ, which is a barrier to interhemispheric mixing, is also the fast elevator for getting the CO2 to the other hemisphere. However, when you look at the first model intercomparison project, you don't need to look, that they all look very different. Okay, we get the same similar things, but you can see the gradients are very different among models. And so we now come to this century, and I want to say that there's been a lot of work in understanding, in improving models and understanding convection, but the range in mixing remains the same, okay? So what we have is here to get sources and sinks, you have a measurement in height. The dashed line is what the gradient, what the model infers. And so if the pink line is the observation, then you would infer this to be the flux. And you can see what happens when you over and underestimate the model gradient. So the new aircraft data, and this is from Britt Stevens' very exciting paper. So now the gradient is here. This is the observed gradient. The zero line is here. So what we have is the models that overestimate the gradient, overestimates the northern hemisphere land sink, and overestimates the tropical, overestimate the sink and overestimate the source if your gradient is too much. So here's the aircraft and the over and underestimate. So now, the new century, we have satellite data, and here I show AIRS, which has an averaging kernel in the mid-troposphere. So this provides for us regular atmospheric measures, CO2 in the mid-troposphere. So this is very nice. So, because before I go there, the aircraft data are very nice, and Steve Wofsy has gone on Hippo from pole to pole and got us profiles of CO2 from the surface to the tropopause, from pole to pole and back, but those are limited campaigns. So the satellite provides us with routine measurements of the upper tropospheric CO2. So what we've done is to assimilate the data into a climate model, which we're running in weather mode. Okay, so we start with an ensemble. In our case, we're running the NCAR climate model, into which in the last century I added CO2 interactive carbon cycle. So here we have the initial condition. Every 6 hours we make a forecast. We run the model free. And then we pull in the observations, and then we do a I apologize to people in least, we do a super least squares fit, okay? Find the optimal fit between the imperfect model and the incomplete observations, and find the best approximation of the atmosphere. So then we go forward again. So what we do that's slightly different from other groups is that we assimilate, every 6 hours we take in 1 million raw weather observations. This is a weather forecasting. This is together with Eugenia Kaune. Those of you who know NCEP reanalysis, you know Eugenia. So we're taking in 10 to the 6 weather observations together with 2,000 air CO2 using the local ensemble transform Kalman filter. Okay, so and we run the model 64 at the time, okay, make a 6-hour forecast and then mash in all the observations and then go again, okay, all 64 of them. So here, the first thing that comes out is you can see I'm just showing you a month here, that if I have the prior, the fossil fuel emission, the land, and the ocean fluxes without the AIRS data, then we haven't. This is May, so this is, if you remember Mauna Loa, that's the top of the seasonal cycle. So when the CO2 is highest. So here is at the end of the decay season. So there's fossil fuel and heterotrophic respiration. So the gradient, so this is what I'm showing is the lower tropospheric gradient, so the surface minus halfway up, okay? So it's higher at the surface than higher up here, and it is the opposite in the other hemisphere. But when we put in the AIRS data, the mid-tropospheric CO2 to constrain the vertical gradient, so you can see in this particular model that I'm using, we overestimate the gradient, so by just a little bit, but it is enough to influence the surface fluxes. So I have to show you this. I have to insist on showing equations. You guys, even though I've been told not to. But here is what goes into a climate model. So you have the conservation of angular momentum, you have conservation of energy, conservation of water vapor, and now we're adding conservation of CO2. Now, the data assimilation, I'm getting the best estimate of the blue stuff on the left-hand side. I'm assimilating the wind, UV, TQP. Okay, I have all the stuff on the left-hand side. But the stuff on the right-hand side, the source terms, so for temperature, we have the short wave, long wave, sensible heat, latent heat, and vertical mixing, turbulent mixing by the clouds. And for water vapor, evaporation, condensation. So CO2 only has surface fluxes. So to get the left-hand side, if you're doing water vapor and temperature, you have a whole gang to help you out. Okay, so this is the residual to get you to the left-hand side. Whereas for CO2, it's a very good tracer of the vertical mixing because all it has is surface flux. So it's a clean tracer to test the vertical mixing. So now that we have the airs data, we can do the mass balance approach, which is something Peter did in 1989. So we have now, for 64 ensemble members, we have the estimate of the wind and the CO2, and this is in mass. So then we have the changeover every 6 hours. We integrate over the vertical. So then the vertical mixing by the clouds goes away. And so then we can calculate the flux here. And I'll show you just one figure. And this is by Stephanie, who's sitting with Zhenji Liu, who did the data assimilation system. She's at JPL, and Stephanie, who's in the audience. So this is what we get, for example, surface fluxes where we have assimilated the raw weather, the CO2, and the in situ sites at Point Barrow, Mauna Loa, Samoa, and the South Pole. Okay, so this is very exciting to me because now I think with this approach, instead of estimating surface fluxes in a globally average sense, this is what the ocean does, this is what the land does, or this is what the northern hemisphere ocean or the southern hemisphere ocean or different regions, now we can do it at the grid level. Okay, so we have, this is August, so this is very nice that we have uptake. This is uptake by the terrestrial biosphere. That is very strong. You can see the boreal forest and uptake by the tropical forest, etc. So we're still working on it. This is, to me, it's a very exciting thing. But if we compare the prior, then what we see is that this is the departure from the prior estimate. Then what we see is that there is a major difference in the tropics where we have strong vertical mixing. Okay, so in the tropics where you have strong vertical mixing, a surface measurement is very much diluted in the entire atmospheric column, and so the signal is very small. Okay, and so if your vertical mixing is goofy, then we have issues here. So we get a much stronger sync. So we have differences between what we had expected, which were pretty good. I'm not, this is, all our prior estimates are pretty good. What we have now is different differences on regions of strong mixing. And so we have, here we have stronger uptake, and that particular grid box is compared to prior estimate, is a 41% stronger sync. And what we have is, so what we conclude here is that we don't know. I'm not going to say that the Amazon is a strong sink at this point, because we're still working on developing this and checking mass conservation and all the other technical stuff I won't bore you with. But this Amazon, not a strong source, is also consistent with other groups that have done inverse modeling that uses tests which has multiple levels, CO2 multiple levels, and with the aircraft data, who also conclude that the Amazon is not a strong source. So their group use large regions, do inverse modeling, and here we show it by grid box. So to conclude, what have we learned? I want to reiterate that there are certain things which are robust, even though we are getting to higher resolution and better information, that the land and ocean each accounts for about a quarter of the anthropogenic CO2. And inferring the regional grid scale fluxes requires information about CO2 in the column. This is difficult always because you look at the beautiful marble and this thin blue line, the atmosphere, it's only 10 kilometers, you know, but it's where all the action is, where clouds, you know, all the energy conversion is in that little 10 kilometers. But the tropical fluxes, what I said before, is diluted in the atmospheric column, and it has impact, very little on impact in the column. And so by taking in the vertical information, we have a better constraint, the CO2, and maybe a net sink of CO2. And harking back to Britt Stevens' result, that the overestimate of the weaker mixing or the too strong a gradient, the northern hemisphere land sink would be weaker than what we had thought at the last century. So I'll end up with this, the next steps. We have airs for CO2. We have three, NASA has 3 satellites. Okay, so OCO has the averaging kernel that's maximum at the surface and decreases with height. I showed you airs, which is a mid-tropospheric, sensitive to the mid-tropospheric CO2, and we have TESS here, and TESS has different levels. So by combining all of these, and I didn't put on here GOSAT, similar to CO2, then we have a way to constrain the vertical gradient. But I want to add that CO2 from satellite is not useful unless we have an ongoing calibration program like TCON and AirCore, which can tie, especially AirCore, that can tie the satellite measurements to Mauna Loa and other surface records. So thank you very much.
I have to stand on my toes to get to the microphone here.
Hi.
That was very interesting, Inez. I'm wondering whether you use the surface and the aircraft data to constrain this inversion, or do you withhold it and evaluate your results afterwards? And if so, what does it look like?
This is very early, but the surface, we have not used the aircraft, and we're trying to figure out how to use the aircraft data at the same time where the satellite data come in. And so we have not used the FLAS data because the FLAS data because I need to know it every 6 hours, and the FLAS data are averaged over 2 weeks. So I don't really know. So that's something that I would be interested, you know, in one of the earlier stuff, we showed the comparison with the aircraft data by assimilating the air CO2. So I can show you that particular paper.
That would be interesting.
Okay.
Also, just another question. Have you guys thought about whether or not assimilating the CO2 will improve weather forecasting? Is that one of your
That
objectives?
was one of the hopes, especially in the Southern Ocean, where we do not have very good wind data, that I can show you how we do the CO2, the correlation between the wind, the U prime and CO2 prime in our 64 ensemble members, that if we have CO2 data, CO2 observations, that we could get back synthetic wind data. So that's one of the hopes, and keep posted, we'll tell you. Okay?
Hi, I wonder what is the resolution of your grid estimation, and I mean the size of your grid cell, and if that can be aligned with the land use change observation from the satellite.
Yeah, so this is the nice thing about right now, this is still in a test mode, so we won't, if we crash, we want to crash quickly, so we know. So this is run, I'm going to say T40 something. So about 2-degree resolution. And once, because this is the by using the Kalman filter approach, it's very easy to plug in and out when the machinery, when we have checked conservation, when we have checked all the other things, it's very easy to go into a higher resolution model, to the newer model, to models with different convections. So it's very easy to do that. But right now we're still in testing mode.